Okay, ladies and gents, before we start our lesson today, I've been asking you to make sure that you have been learning your definitions. So I'd like for you to get a piece of paper for yourself and write for me a definition of atomic radius, of first ionization energy, and state and explain the trend in first ionization energy across a period. You don't need to put your name on it because you are going to be uploading it to the class notebook homework page for this assignment. So press pause, get it done. You can upload it later. Okay, so now that we've done that, today's lesson we're going to look at why the increase in ionization energy across a period just doesn't go up in a straight line. So we remind you the last day of the graphs that we drew, and we get these blips, and this is us going across a period. So it's why do those blips appear. So you have this graph, it's roughly on page 130 of your yellow notebook. It matches the graph that you drew out earlier in the last lesson, and we just need to do some things now to it again. So you need to have a look and label things that end in S2. You need to label the elements that end in P3, and you need to label the elements that end in P6. So take the time now, pause to do that, and then we'll have a chat about it. So the first blip down here are our S2 elements. This second blip here are our P3, and the top, or the peaks, or the top of the line, are all P6. So just to remind ourselves, here going from helium to argon is going down a group, and ionization energy decreases down a group because your atomic radius increases, because there's an increase in energy levels and an increase in screening. And going from lithium all the way up to neon is going across a period. And here our ionization energy is increasing, and the reason for that increase is because there is a decrease in atomic radius, an increase in nuclear charge, and screening is constant. So now we're going to look at the questions. So the first question is the things that end in S2. Why are we getting these particular peaks? So this first little blip means that the ionization energy of the S2 are higher than P1, and it means that because it's higher, it's more difficult to remove that outer shell electron. Okay, so they have the full s orbital, and full s orbital gives stability. So that is the reason why the ionization energy is higher. So ionization energy is higher because it has a full s orbital. It makes it more difficult to remove that outer shell electron. If we have a look at the P3, so this is our second blip. So now in terms of the description, so the elements at the P3, it's much higher ionization energy than elements at P4, and the reason for that is because they have 3 half-filled p orbitals. So 3 half-filled p orbitals have greater stability than partially filled p orbitals, and the ionization energy is higher, and again it's harder to remove the electron from a P3 than it would be from P4. And then finally in our P6, why do we get the peaks that we get? So these are the electrons that are hardest to remove, so the outer shell electrons, and the reason being is that they have 3 full p orbitals. So the fact that you have 3 full p orbitals makes it really hard to remove that outer shell electrons, and this is by far the most stable configuration. Now, you may have a little bit of room for this, but helium has a ridiculously high first ionization energy, and it goes back to the fact that it has a very small atomic radius. It has no screening from the nucleus because all the electrons are in the first energy level, and it has a full s orbital. So when we draw helium, if this is our nucleus, this is where our electrons are. There is no screening, so it's going to be really difficult to remove the electrons from helium. Now, the fact that we have these irregularities or these peaks, we learn from them that filled orbitals are the most stable derangement, and that half-filled orbitals, particularly p because there's 3 of them, they are the next most stable. So filled orbitals, they will have a very high ionization energy, and the half-filled orbitals, they'll be slightly lower in ionization energy. So this is why we see peaks at these points in the graph, and just more stable usually translate to a higher ionization energy, and it means that it's harder to remove the most loosely bound electrons. So in the outer shell, one of those electrons, it's going to be really, really hard to remove. Now, I'll leave you read this. So ionization energy can be really hard to get your head around, but you help yourself by firstly knowing your definition, by knowing your state and explain, and then you break it down to the blips. Why do we get the blips? What is the reason for it being slightly higher in ionization energy than the element that comes after it? In terms of the graphs that we've looked at, you need to make sure you understand the graph to date. So what is the information that it gives you? So it tells you what happens across a period, it tells you what happens down a group, it tells you the electron configuration for the blips and how that can be related to ionization energy. There's one other graph and it looks like this, or a version of this. And the question that they ask for this type of graph is, how does this provide evidence of energy levels? So we've done our electron configurations, the little diagram is here. So why do we have a 1s? Why is there 2s and 2p in our second energy level? Why is there 3s, 3p, 3d in our third energy level? And how does this diagram prove that? So the first thing that we're going to have to figure out is what element is it? So this is showing you the log of ionization energy, and this is showing you essentially number of electrons. So can you work out what element this might be? So if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. So if you're 11 electrons, you must be a sodium atom. So that's the first question, what element? So how many energy levels can we see from this particular graph? So there are 3 distinct areas in this graph suggesting 3 energy levels. And if this is showing ionization energy, and the definition is minimum energy required to remove the most loosely bound electron. So where is the most loosely bound electron? Is it on the left or is it at the top right? So hopefully now you are saying that the electron configuration for sodium is 1s2, 2s2, 2p6, 3s1. So knowing that, this must be 3s1. This must be 2p6, p3, and this must be s2. So this is 3. So we're working backwards. Am I incorrect in this? I am incorrect in that, so I apologize. Let's just rectify that. This is obviously energy level 2. So this is 2, 2, and 2, and here this must be 1s2. So what we can see from this is each time we remove an electron from sodium, it is getting harder to do it. The ionization energy, the energy needed to do it, is getting bigger. So we can also see, because of the 3 lines, that there are 3 energy levels here. So that is another piece of information for us. So this is answer to question 2. It shows 3 energy levels. And we know from this that every time an electron is being removed, your ionization energy increases. We can see that it's really easy to remove the electron from the outer energy level down here. And that once we get into energy level 2, there is a really big jump to remove from energy level 2, and even bigger again to remove from the inner energy level, the one that's closest to our nucleus. So the other just piece of information I'd like to just put in here is, for this, if you have removed this particular electron, you would have a 1+ charge left over. Similarly here, you're now going to have a 2 positive charge, 3 positive, 4 positive. You'd have 5 positives here because you've lost 5 electrons at this point. 8 positives here because you've lost 8 electrons. And finally up to here, when we get to here, we would have an 11 positive. We'd have lost 11 electrons once that electron would be removed. So that's very similar to saying increasing nuclear charge. So increase the nuclear charge, you increase your ionization energy, because now these protons are sucking the remaining electrons to themselves even tighter, which is why it needs more energy to remove them. So that's the end of this first little section, and obviously this should read ionization energy. Don't know how that got away. And the last little bit we just have to look at is something that we looked at when we started back in periodic table and atomic structure, where we looked at the reactivity down group 1. Remember, we went outside and we put sodium metal into water. I think we started with lithium. We put sodium, potassium, couldn't do rubidium, cesium or francium, and we found that there was a reactivity once you went down the group. So hopefully by now you know that as you go down the group, reactivity increases. And we now have to figure out why that is. So everything in group 1 is going to have similar chemical properties. And why is that? What is it that everything in group 1 has in common? Well, they have the same number of outer shell electrons. So these guys will all end in S1 as their electron configuration. So if reactivity is increasing down the group, what do we now know from our trends lessons to date? So we know down a group something happens to atomic radius, and we know the reasons for it. And we can use those exact same things to explain why reactivity increases down group 1. So as you go down group 1, our activity this may not be included in your notes, but the atomic radii of the elements increases. The number of energy levels and screening increases. And that will allow them to lose their outer shell energy levels more easily as you go down. So again, going back to ionization energy, that's going to decrease. So the reactivity is due to the size of the atomic radius and how good that is at holding the outer shell electrons to itself. So the further away you are from the nucleus, the easier it is to lose electrons. We did a similar thing with group 7, so I couldn't show it to you. So this is group 7, and in terms of reactivity, group 7 is weird because reactivity increases up the group. So fluorine, we're going to come on to electronegativity. Fluorine is the most electronegative thing. So what that means is it pulls electrons to it, and it's the most electronegative thing on our periodic table. So It is more reactive up the group, but if you have to describe reactivity, we would say it is less reactive down the group. So again, why does it work differently to group 1? These guys aren't going to be losing. So in terms of outer shell electrons, these would have 7 electrons in their outer shell, and for them it's easier to gain 1 than to lose many. So this is one of the reasons why their reactivity is different. And again, we know about atomic radius. So as you go down your group, your atomic radius increases, your screening increases, and it just makes it harder to gain the electrons as you go down the group. So when the element is small, the outer shell electrons are close to the nucleus, as which happens in fluorine. It makes it much easier to gain that 1 electron, and therefore fluorine is more reactive. In our last part, we looked at group 0, so the noble gases, and we had started talking about increase in boiling point. So as you go down the group, all groups, not the noble gases, but we're going to look at the noble gases because these guys exist as atoms, they don't exist as molecules, so single particles as illustrated here. And as you go down a group, you're getting your bigger atoms, and again it's going back to the blurb we've already done. You've got increasing atomic radius, increased number of energy levels, and increase in screening. And in terms of boiling points, and we're going to be coming on to this in a little while, we have more electrons if you're a bigger molecule or bigger atom, and we have this thing called van der Waals forces. So what van der Waals forces is the force of attraction between 2 different atoms, and the bigger you are, the more attraction you actually have for other atoms around you, so therefore you have a bigger boiling point. We will come back to this again, so please don't worry on that front. Now for today, you need to take photos of your notes and you need to put it into the class notes section. So there is no link for this, you find it through OneNote, it's in your section and it'll be headed class notes. There are homework questions in the assignment in class notebook page, so you need to put that work in there. I am currently on Zoom waiting for you if you have any questions, and we will move to a revision lesson for our next lesson, and in my head we're aiming for an end of topic on this on the 1st of February. So we'll see where we go. Get in touch if there's any problems. Thank you.